All right, today we're going to do 9.1. I don't know, say today, whatever day you're watching this video. So anyhow, we're going to start something called significance tests. So we've done confidence intervals, and now we're going to do something called a significance test. It's there's a lot of similarities, and they're in some ways they're different, but you'll see how it works. This probably shouldn't be too bad, and we'll maybe try to over-explain some of the big important topics that we need to do. And hopefully this video will come a little bit nicer. I got a little phone holder instead of having it stacked on a group of cans. So we'll see how this goes. All right. So we don't have this printed out. Notes here are kind of long enough, but it says you have two explanations why X bar isn't 98.25 instead of 98.6. So 98.6 is what we consider to be the regular body temperature of a human being if you're not sick. Or haven't been exposed to elements or whatever. We run at 98.6 degrees. So in this problem, a person did a random sample. And again, they talk about everything done properly, but they did a random sample of so many people. I don't remember how many it was. And they found out that the average temperature was 98.25. So then the question is, well, why is that? So the first thing is, and we know this from the way we talk about sampling, is that it could be chance variation due to random sampling. You take a sample, I take a sample, he, she takes samples, whatever. The samples are not the same. All right, so there's going to be, we have to allow that. We have a margin error. Well, I better not say margin error. That's for the intervals, but same basic premise here. We have to allow some variance because of chance variation due to random assignment. Okay, or there's another reason, and that they're lying. Or they're wrong. I guess it doesn't have to be a lie. They could just be wrong. Maybe the average temperature isn't 98.6. So there it is. And then this next one, said I think this was the potato problem, which I think we come back to later. But they said that they throw out the potatoes if it's 50% of them are bad, or 50%. Yeah, maybe that's what it was. I don't know. And they end up getting 62.3%. Okay, now the difference between 89.6 and, oh my gosh, 98.6 and 98.25, that's not a very big difference. Now we talk about temperatures, you only have to be like a temperature or two off and you got a fever, and you get a couple more degrees and it's a pretty significant fever. But we're talking not even a half, right? Not even a half from those. Well, this one is 62% versus 50%. And again, the story behind it, who cares? But that one, we're probably not going to say it's because of chance variation due to random assignment. If we're claiming it's 50% and we took a sample and got 62.3, yeesh, that's a little bit far, okay? So again, it could be chance variation due to random assignment, but probably not, or we have reason to doubt the claim of 50% for whatever it is. All right, and then one thing we can do is, again, what they call a significance test. So here we go. Excuse me. In a recent study, relative age effect and career success. Boy, that sounds like fun. Evidence from corporate CEOs suggests that people born in June and July are underrepresented in the population of corporate CEOs. This is consistent with the relative age effect due to school admissions grouping together children with the age differences up to 1 year. Yeah, that's wonderful. With children born in June or July, children born in June and July disadvantaged. So they're basically saying they're gonna, they're kind of jamming them in or they're keeping them out. Is that causing problems to students? So then they took a sample of 375 corporate CEOs and only 45 or 12%. So that's less than you would expect it to be. You would expect it to be about 1 out of 6, 16, 17%. This one's 12%. And that's a pretty good size sample right there too. But anyway, is this convincing evidence? So give two reasons why the proportion is less or is below 2/12, chance variation due to random assignment, or the true population proportion, the parameter, is not in fact 2 out of 12. So then we could do a simulation, which of course we don't want to do that. That's why it says thankfully, or we can do something called running a significance test. All right, here we go. So the first thing we're going to have to do is we're going to have in our, well, we'll do this in a second, more formalized, but this state step, it's still state, plan, do, conclude. The state step, you will state a null and alternate hypothesis. Now, that's a lot of big words and it seems scary, but H sub 0 for the null hypothesis, H sub A for the alternate hypothesis. Okay, this is this is not the book's words, these are my words, what they claim and what we believe. Okay, now that doesn't work for every single problem, okay, because there was no claim being made in the CEO problem. So another way to think of it, and this is more in line with what the book has, but this helps us more as we're starting out based on most of the word problems, but the statement of no change, okay? And then inequality for alternate hypothesis. And if you're like, well, what the heck does that mean? It means the null hypothesis is going to be that P is equal to something, no change, statement of no change. It is equal to 2/12. And you might be thinking, well, wait a second, they claimed it was underrepresentative. And that's why the they claim and we believe is not always the best way to state that. It is a lot of the time, and it's a good way without, not as a definition, but for us in our brains, it's a good way to think of it. Anyway, so then we're trying to show that it's actually less. And the null hypothesis always has an equal within the context of this class. All right, the next one, Mike is a golfer and he had a brand new 7-iron. And then, let's see here. Originally he had an average of 175 with a standard deviation of 15 yards. And so he wants to see if it's any better. And then he's gonna check that out. So the null hypothesis is that the standard deviation is 15. The alternate is that, because it said he wants to see if his new club is better. So then therefore there should be less variation. In golf, it's not necessarily usually how far you can hit it. It's how accurate you can hit it. So standard deviation would be a big deal. All right, and then what's the difference for a two-sided and a one-sided alternate hypothesis? We will talk about two-sided and one-sided, but for right now, one-sided is if we're saying that P is greater than or less than a certain value, or mu for a problem, P for proportions, mu for means. A two-sided is going to say when they're not equal. So too big or too small would be a problem or something that we want to avoid. All right, what is the p-value? All right, here, this is a big one. This is a big deal, but this is the probability that if the null hypothesis is true, that we got the sample in the problem. So if the null hypothesis is that 50% of students in AP stats are boys and 50% are girls, and I take a sample and I get 6 boys and 4 girls, or 6 girls and 4 boys, okay? So then I would run a hypothesis test and I would get a p-value, and let's say the p-value was 0.3. That would be if in fact it is truly 50-50, the chance of you getting a 6-4, 6 girls, 4 boys is 0.3 or 30%. And you'll never guess what the cutoff is. It's 5%, just like we've been leading up to all year. Okay, but if in fact the null is true, the p-value tells us the probability that we would have got the sample we got, or one that was even more extreme. So 6 girls and 4 boys, or 7 girls and 3 boys, or 8, and it adds all those up together. We don't have to do this. The calculator is going to do all the work for us in this one. We just need to understand what to write based on what the calculator tells us. All right, so in the CEO, the p-value was 0.008. Interpret this value. So the probability, yeah, I like this. Oh no, right here. The probability that our sample would have been less than 12%, given that in fact it's 2 out of 12, which again, that's 1/6, that's like almost 17%, is 0.008. If in fact they were in true equal, every month was equally represented, the probability that we got this crazy sample that we got in the problem is less than 1%. If the p-value is less than 5%, then we will reject the null and we have convincing evidence that the alternate is true. Now, again, you don't say the alternate is true, you say it within context. Now, that's something we're going to have to get used to, but if the p-value is small, then we reject the null hypothesis because there is evidence that the alternate is true. And I'm sure we'll get this here in a minute, but if the p-value is bigger than 5%, you do not accept the null. You fail to reject it. And as a matter of fact, if you ever say accept, then the whole problem is 100% wrong and you deserve it. That's just a fair warning right there. All right, going back to the irons problem with the golfer. So Mike takes his new 7-iron out and he shoots, I guess it doesn't tell us the sample size. I don't know why, but he goes ahead and he shoots, I don't know, maybe it said in the last problem. He takes several shots and he calculates that his standard deviation is 13.9 instead of 15. Okay, now the question is that enough of a difference to prove that this new iron is in fact better? Okay, so I'm just going to skip down this. Significance test shows a p-value of 28%. If in fact it's the same, that both the new and the old club have a standard deviation of 15 yards, that means the probability of us getting a sample that was 13.9 yards or further away from 15, so in this case, or less, the probability of that happening, if in fact it is true that it is equal, the probability that we would get this result is 28%. It's about better than 1 out of 4. So even if the club had no effect 1 out of 4 times, he would get that result, or one that was even more extreme. And that's not enough evidence. So the probability, I just said that. Since the p-value is greater than alpha, and we'll talk about alpha here in a second. Sorry, I don't know why, just 0.05. Shouldn't have said alpha. Then we fail to reject. So I don't accept the null. I fail to reject it. I either reject it or I fail to reject it. That's it. If you say accept, I'm going to count off the whole write-up is completely wrong and then post it on the internet and all your friends are going to laugh at you. Probably your parents too. Since the p-value is greater than 5%, we fail to reject. There is not evidence for the alternate. Okay, that part of it, that's what the conclusion is going to look like. That second, not this top sentence, but this bottom one. Since the p-value is greater than 0.05, we fail to reject the null. There is not convincing evidence that Mike's efficiency is better with the new golf club. Okay, and then now some over-explaining. 2 possible conclusions. You reject or fail to reject. Never, ever accept. That's not newer. That's a V that's attached to the E for some reason. Okay, if the p-value is small, then we're going to reject the null. Okay, there is evidence for the alternate. If the p-value is not too small, then we fail to reject it. We don't have the evidence that says that the null is, or we don't have enough support to reject the null. And again, don't say we accept the alternate. You say that we have evidence to suggest that the alternate is true, but you don't accept it, and it doesn't prove it either. It's just convincing evidence. Okay, some common errors. This one is from the textbook. This is the AP, says the most common errors. The first one is to say accept. I believe I've over-explained that one enough. The next thing is when we do these problems for all chapter 8 and chapter 9 and chapter 10, you will not be writing X bar or P hat for your write-ups. You're going to infer to the population. You're going to infer to P or mu. Oh, yeah, then this one here, the null hypothesis, you do not make the null hypothesis based on the sample. You make it based on the wording of the question. So there you go. Sorry, got a little forgot myself for just a little bit there. All right, what is the significance level, and when are the results of the study statistically significant? So remember a bit ago I was calling the 5%, I called it alpha. There it is. Okay, and alpha, by the way, it's typically 5%. So alpha is a fixed value that establishes as statistically significant. Whatever we can make the significance level 10%, 5%, or 1% are the three numbers that are used 99.999% of the time. All right. Whatever that value is, your p-value needs to be lower than that to reject the null hypothesis. When you reject the null hypothesis, that's statistically significant. Say, why do they call it statistically significant? I don't know. They just do. Deal with it. All right. For a second semester project in AP Stats, Zenon, I love that name, by the way, decided to investigate whether students in his school prefer name brand potato chips to generic potato chips. After collecting the data, Zenon performed a significance test using a hypothesis that the null says that P equals, and again, notice the null has equals and the alternate is an inequality. Okay, so that the p-value is 50% or the p-value is greater than 50%, where p, and you'll have to do this too, you'll have to define p right after it, where p is the true proportion of students at his school that preferred name brand potato chips. So if it's over 0.5, more than half the kids prefer the name brand. If it's under 0.5, then they don't care. Then more than half don't care. Or they prefer the store brand. Nobody prefers the store brand except for the ones that have the yellow cheese on it, because a lot of times the store brand has too much cheese, and that's why they put those in the store brand bags instead of the Ruffles or the Lay's bags. I like that. All right, so now the next question is, what happens with the different significance levels? So here the p-value was 7.4% or 0.074. If alpha was 10%, the p-value is less than alpha. If alpha is 5%, the p-value is greater than alpha. Okay? So if we pick 10%, we would reject the null hypothesis and say there is convincing evidence that the students prefer the name brand potato chips. If we pick 5%, we'd say that the p-value is bigger than alpha. We do not have convincing evidence that the kids prefer the name brand potato chips. Okay? That if you're really thinking and paying attention, that should make you scratch your head and think for a second and go, wait a minute, what's to take any statistician to change the numbers to suit their needs? And I've told you guys this from the very first day. You will learn how to lie without technically lying. It's a great skill to have. There's a lot of money in that. Okay, so which one do you pick? Okay, well, sometimes it depends on, like, is it worse to suggest one or the other? Okay, or in this case, it would be who's cutting the checks. Okay, if you're working for Lay's potato chips, then 0.1 is the answer. If you're working for the school, or you work for Kroger or Walmart or any of these companies that make the cheaper potato chips, or maybe you don't like spending money, or maybe you're a parent and you're tired of your kids spending $8 a day at lunch. You're like, get the freaking Lay's out of there and put in Kroger potato chips and save me $1 a day. That's fine. They don't care about the chips. They all taste about the same. 5% would be your alpha. Again, just like when I said before, every time you see a diagram on a commercial, like a picture or a table, it's a lie. Okay? Same thing with this. Okay? Unless it's so bad, maybe it's 28%, it doesn't matter if I pick 5 or 10. If it's in between 5 or 10, it absolutely matters. We don't get into this huge in this class, but I like to point this out because this is the type of stuff, this has nothing to do with AP, well, yes it does. Besides AP Stats, this is good stuff to know. Be like, no, we have statistical analysis that says this is true. Like, yeah, really? Well, where were your statisticians employed from? Oh, they're employed from Lay's potato chips? Yeah, your data is of no consequence to me. And any political data is typically, I'm not picking sides. I have no side. They're all idiots. But the political ones are they're the guaranteed. If you see a stat or a number on a politics thing, it's all lies every time. All right. Next thing, type 1 and type 2 errors. So we're going to talk about this some today. You're not going to like type 1, type 2 errors. Students hate this stuff. We'll talk about it. We'll go over it, and we'll see how it goes. Maybe for the test, with it being open notes, that should help. But for the AP exam, we'll see. In a jury trial, there's two types of errors. We could let a guilty party walk, or we can convict an innocent person or party. Okay? A type 1 error happens when we reject the null hypothesis when in fact the null is true. Now, we won't be able to know the null is true, but we're going to reject it based on our data. And again, we don't do anything wrong. It's just the data. Sometimes we get data. We get those crazy cases. You get the crazy case when you ask kids how many pairs of shoes they have, and everybody in your sample owes 60 pairs. When that's just not the average number of pairs of shoes that people own. Just that's how it works sometimes with collecting data, okay? Type 2 is when we fail to reject, and in fact, you should have, okay? And the only way I keep these straight is fail to reject. You see, I use the Roman numeral 2. Type 2, fail to reject. That's all I got for you. And then which one's worse? It depends on the problem. Now, with that, a lot of times it's insanely obvious. Like, for example, money is not as important as the health of people. Now, your money versus the health of somebody you don't care about, we're not talking about that. But if they want you to pick a side, it's going to be really obvious which one's worse. If it's iffy, then you pick one and back it up statistically. Something that would make your stats teacher happy for you to give the reason why. But and on this one, if we talked about which one's worse, it kind of depends on the crime, does it not? It also depends on who's on trial. If it's your mom, that changes it versus if it's some person that's, on their third strike and they're out type situation. It depends on the problem, okay? Personally, if it was me and I was on trial, I think it would be way worse to convict me when I was innocent, because I'd be the one going to jail, okay? And again, then it kind of depends on, again, we'll get into that. Also, I'll tell you right now, sometimes they use situations to invoke an emotional response. So I apologize if it hurts anybody. I remember we used to always use cancer, and finally when somebody came up and said that their grandparent just died of cancer, and that could we come up with something else maybe for the test, because that's all I had ever been using. So sometimes it'll be about that, but then again, it's to make it's really obvious which one's worse. Like when we're talking about cancer treatment, detection of cancer, it's really important that we find it over worrying about how much the test cost. Okay. Two more things real quick. A little bit long on this video today. All right. Describe a type 1, type 2 error in the CEO problem. Which error could the researcher have made and explained? Okay. So a type 1 error would have been, and this is not part of your answer. I just wrote that in there on the notes to help. Do not write that on your test answer. Okay. This is just a note in the parentheses for me. And again, type 2, fail to reject. We claim that the June and July birthdays are underrepresented when in fact they aren't, okay? So we rejected it and we said the alternate is true, that they were underrepresented, but in fact, that wasn't the case. A type 2 is we declared that they are not underrepresented when in fact they are. Now, here's what I was talking about. Well, which one's worse? Who cares? Like, what difference would it make? This one, there's nothing that would indicate why one would be worse than the other. If they ask you to do that, you pick one and you come up with something that you think an adult would want you to say if you have nothing else. Hopefully, like I said, if they ask you to pick one, it's going to be very obvious. But that's not how the College Board works. Sometimes they do that stuff and you have to be ready for it. And also, let me warn you, type 1, type 2 errors, students miss this stuff. They just butcher it. So you're definitely going to want to practice this some. All right, probability of a type 1 error. What is the probability of type 1 error? And it's always whatever alpha equals. To be honest with you, most students just plug that in their head and remember that. Multiple choice question. I'll give you a huge paragraph with all kinds of crazy information on it. And I'm not kidding, tons, like a huge paragraph, lots of big words. And at the bottom, they'll say, oh, the significance level was 10%. What's the probability of a type 1 error? You don't need to read any of that other stuff. All you needed to see the significance level was blank. And that's what alpha is, the probability of a type 1 error. How do you reduce the probability of a type 1 error? You reduce the significance level. So if I have 5% for my alpha and I want less chances of a type 1 error, maybe a type 1 error would be very, very, very bad. So then I would need to make alpha 1%, which would make it harder to reject the null hypothesis, but it would also make it less likely that we reject when we shouldn't. You can also increase the sample size to reduce anything that has anything with variability. Increasing the sample size would work as well. And one other thing, the probability of a type 2 error, you can raise that. Now that's kind of weird. What I need you to know for this is as the probability of a type 1 error goes up, the probability of a type 2 goes down and vice versa. All right, there's the start of chapter 9. The next videos will not be as long. Take it easy, y'all.